Hi there, welcome. As promised, in this week we start our mini course on survival analysis. We will see that survival analysis is a very nice way of modeling, of studying the probability of default and loss given default. Now, survival analysis is a branch of statistics that deals with the study of the random time at which a specific events or a series of events manifest itself. The typical example comes from biostatistics, where we are considering the lifetime of individuals. So, in survival analysis, we typically have two states, A and B, and we are interested in the event that governs the transition between the two states. So, the state A can be life, state B can be death, and we are interested in the time in which we have the transition. So the individual we are considering dies. Another example, more close to our field, is when we are considering a company. This company can be in two states, just to simplify, non-default and default. So with survival analysis, we will study the random time at which we observe the transition, that is to say, the default. Obviously, we can have a lot of other applications, and survival analysis is a very important part of both biostatistics and reliability theory in engineering. Now, in the usual setting of survival analysis, we then have a random variable capital T, which is a continuous random variable representing the time at which we observe the transition from state A to state B. So it's the so-called time of the event. For us, it will be, for example, the time of the default. We then call small f of t the density of this random variable, and with capital F of t we indicate its cumulative distribution function. A fundamental object in survival analysis is the survival function. Now fix at time small t, the survival function gives us the probability of surviving at least until time small t. This is equal to the probability of our random variable capital T to be larger than equal to small t. And this probability can be expressed in terms of the CDF, the cumulative distribution function capital F. In fact, this is equal to 1 minus the probability of not surviving until time small t, that is to say 1 minus f, capital F, of t. On your screen, you can see two typical examples of survival function. One, it's an empirical one, in particular the one that we can obtain using an estimator. We will see together the Kaplan-Meier estimator. And the other one, the continuous blue line, can be a theoretical one. And this is, for example, what we can obtain when we use parametric or semi-parametric approaches. Given the survival function, we can define another very important quantity, the hazard rate. The hazard rate gives us the rate at which a system surviving at least until t changes its state exactly in t. That is to say, assume we are considering a company, we know that our company has survived until t, so we have seen no default for that company. Okay, the hazard rate tells us what is the rate at which that company will default exactly in t given the survivorship until t. The hazard rate is defined as the ratio between the density f of t and the survival function s of t. Now, it's easy to see that the density can be written as nothing more than minus the derivative of s of t with respect to t. Remember that S of t is 1 minus capital F of t, and this is the way in which we represent the hazard rate. If we multiply the hazard rate lambda t by an infinitesimal time interval dt tending to 0, what we obtain is the conditional probability that our company, for example, will default in the time interval t plus dt, given that it has not defaulted until time t. Taking the integral of the hazard rate until time t, so from 0 to t, we can define the so-called cumulative hazard function. It's easy to see that there is some nice relationship between the survival function and the cumulative hazard function. In particular, the survival function is equal to the exponential of minus the cumulative hazard function. So, how can we model the probability of default of a counterparty using survival analysis? We first have to define the setting. So, in this situation, the random variable capital T represents the random time at which we observe the default of the counterparty, more or less as we did in the Lees model. Do you remember? For what concerns the survival function St, this will give us the probability of not defaulting until a time small t that we fix or that we want to study. And finally, lambda t, the hazard rate, will give us the instantaneous rate of default for our counterparty, given that our counterparty has survived until time t. When we deal with the modeling of the loss given default, the event itself is no longer the default of the company, but the full recovery of the company. So capital T is now the random time at which we observe the full recovery. So the recovery process is over. With capital F of T, we represent the expected recovery rate at time small t, and with the survival function capital S of t, we represent the expected loss rate in t. Remember that St is equal to 1 minus capital F of t. For what concerns the hazard rate lambda t, this will be the speed of recovery on the unrecovered amounts at time t. In this mini course on survival analysis, we will consider together different approaches, some parametric like the Weibull or the log logistic models, some semi-parametric like the very important Cox model, and some non-parametric like the famous Kaplan-Meier estimator. But before introducing this last tool, the Kaplan-Meier estimator, we need to say something about a peculiar characteristic of survival data, that is to say, censoring. Censoring occurs every time we are not able to really assess the time at which our event took place, for example, the default. Consider the 4 companies on your screen. Company 1 and company 3 represent no problem for us because we can observe T1 and T3. But for company 2 and 4, we have problems. For company 2, for example, since we are making our evaluations today, we have not yet observed the default. But this does not allow us to say if the default will happen tomorrow, in 1 week, or in 10 years. For what concerns company 4, on the contrary, what we have is that somehow this company has disappeared from our dataset. So the time we observe, the final time we observe, is not really the default time, but just a time at which the observation has been censored. To be more precise, what we have just described is what statisticians call right censoring, because we are censoring the end time. Naturally, you can imagine that sometimes we have left censoring. For example, we don't know, but this is quite absurd in our case, the time at which a company entered our portfolio or the time at which a company was founded. This is something that happens much more frequently in survival studies in biostatistics, where it can be difficult to assess the exact age of a patient entering the sample or so on. At due time, we will see that we need to pay some attention when dealing with censored observations. That, I repeat, for us will essentially be right censored observations. Okay, let's conclude this class by saying something about a simple but fundamental tool in survival analysis. It's a non-parametric estimator, and it's the Kaplan-Meier estimator. On the course platform, you will find some extra details for the computation of this estimator using R. The Kaplan-Meier estimator is a non-parametric estimator for the survival function. It is defined for both censored and not censored data, and in practical terms it is represented as a series of declining horizontal steps that approaches the true survival function if the sample size is sufficiently large enough. The value of the empirical survival function that we obtain with the Kaplan-Meier estimator is assumed to be constant between two successive distinct observations that are often called clicks. Consider n companies, and for a k smaller than equal to n, take into consideration the event times t1, t2, tk that we have ordered. Now, let nj be the number of companies still active just before time tj. In case of no censoring, nj is just the number of survivors. In case of censoring, nj will be the number of survivors minus the censored observations before tj. With dj, we indicate the number of companies experiencing the event, say for example the default, at time tj. The Kaplan-Meier estimator for the survival function capital ST is represented by S hat of t, and it's the product for j such that tj is smaller than equal to t of 1 minus dj over nj. Notice that 1 minus dj over nj is nothing more than the proportion of survivors at time tj. This is the simple but extremely useful Kaplan-Meier estimator for the survival function. I thank you for your attention and see you next time. Goodbye.